We've been talking about pi bonds, CC pi bonds attacking carbon electrophiles to make new CC bonds, which is really that's most of what organic chemistry is about for typical organic chemists is how do we construct carbon-carbon bonds. And we spent a lot of time talking about how long bonds or anionic atoms, bonds to anionic atoms like borate, aluminate, siliconate, can really soup up the nucleophilicity of CC double bonds, but really lone pairs are where it's at. And so we've been talking now about enols, enamines, and enolates, which have lone pairs right next to the double bond. And those lone pairs donate into the pi star system and create a new pi-like orbital that's much more nucleophilic than just a regular alkene. So when we left off, we were talking about the use of lithium diisopropylamide, developed in the 1970s, late 1960s, I think, sometime in that period, and it just completely revolutionized the field of aldol reactions because it allowed people to make regioselectively deprotonate next to carbonyl groups. So remember, LDA, it's not just the use of lithium diisopropylamide, there are these special conditions where you add the ketone to the LDA. You don't add the LDA to the ketone, because if you add the LDA slowly dropwise to the ketone, you'll have excess ketone floating around that can act as an acid and catalyze isomerization. So LDA, we never have an excess of the ketone while we're deprotonating. Each drop of ketone lands into a sea of LDA and is instantly deprotonated. With selectivity, because of this chair-like transition state that we talked about, this six-membered ring transition state called the Ireland transition state, you want to deprotonate so that you minimize interactions between the isopropyl groups on the LDA and this R group that is on the alpha carbon. So this allows us to stereoselectively make enolates where the alkyl substituent next to the proton that gets deprotonated ends up anti to the oxygen atom of your lithium enolate. So that's powerful, that you can regioselectively deprotonate on the less hindered side and get this enolate geometry, so controlling stereochemistry of enolate formation and regiochemistry at the same time. Now, lithium plays a critical role here in organizing this six-member transition state, but it's not over, because why do we make lithium enolates? So sometimes we alkylate them in SN2 reactions, but that's not typical. That's not typically what we do with a lithium enolate in the field of organic chemistry. Usually when we make lithium enolates, we're converting those, we're using those for aldol reactions. Let's go ahead and walk through a mechanism for an aldol reaction. And instead of using the lithium enolate to attack sp3 carbon, what would happen if we use that lithium enolate to add to a carbonyl group? So this is called an aldol reaction, right? You add to a carbonyl group, and it makes a new CC bond, and that's powerful. And this is the way that biology makes bonds. This is the way all the bonds in your fatty acids, all 18 carbon, all those bonds in the fatty acids are assembled using these types of aldol reactions. Now, when I look at that lithium there, when I think about, gee, what's the reactive component here? I see this nucleophilic carbon that I've highlighted in yellow, but that lithium atom, that thing wants 8 electrons. It's only got 2 electrons there. We don't want that. So the first thing that ought to happen here, just like with that deprotonation to make the lithium enolate, the first thing that should happen here is something should coordinate to that lithium. Right? Lithium wants 8 electrons, not 2. So let's go ahead and draw out that complex that we would get. Now, you usually do these reactions in ether solvents. So it is true that ether molecules are coordinating to the lithium, coming off the lithium, coordinating to the lithium, coming off the lithium. That's happening. It doesn't affect what's going on in the reaction. What we care about is that moment, that instant in time where the carbonyl of our aldehyde coordinates to that lithium, forms a bond to lithium. And we're going to be perfectly set up now to make a CC bond, and just everything looks wonderful here. I've got this T-butyl group. Now look at that. I've got that nucleophilic bond there. Let me fix my charges. I didn't finish my charges. I've got that nucleophilic bond here on my enolate, and it is poised 6 atoms away from the carbonyl of the aldehyde. And it's not just an aldehyde now. It's the aldehyde oxygen has a positive charge and it's an oxoniamine. This is more reactive over here. This carbon is now more reactive than a regular neutral C double bond O. And this enolate is more reactive because it's attached to lithium minus. And so you get this very fast and very facile CC bond forming event. This is really what's going on with an aldol reaction. Goes through that 6-member transition state in order to make that new carbon-carbon bond. Look at that carbon-carbon bond right there. Boy, so easy to make when you're using lithium enolates because of this special 6-member transition state. Now, we've already talked about similar looking 6-member transition states. You may remember, I don't know how long it was ago, about a week ago, we talked about allyl boron compounds. I showed you some allyl boron compounds where we had carbon-carbon double bond attached to boron, and we said, oh yeah, we expect oxygen to coordinate with boron. Boron wants 8 electrons. That makes sense. Of course, a carbonyl would want. Same thing with an enol boronate. Same thing with an enol boron ester. Right? Even if this is oxygen instead of carbon, we'll still see this same pattern of reactivity. And so after the development of lithium enolates, people developed these enol boron compounds, these species, for doing aldol reactions. And it works in the same way as the lithium enolates do. You get this charge acceleration of that CC bond forming event. It becomes boron minus, it becomes oxygen plus, and so now you've just completely souped up the nucleophilicity of that enolate species. You've souped up the reactivity of the carbonyl group, and so you can't stop these from undergoing just a fast and facile aldol type reaction. Aldol, I would still call that an aldol reaction, a boron aldol reaction, in order to generate a new CC bond. Man. Right? Everything just, it all starts to look kind of the same after a while. Aldol, lithium aldol reactions, boron aldol reactions. Yes, you can do this with other metals as long as they can form an 8 complex, an anionic 8, and coordinate to a carbonyl. There's nothing special here. The basic principles are the same. We're souping up the nucleophilicity of a pi system at the same time as we're souping up the electrophilicity of the pi star, and the reactive atoms are 6 atoms away. Wow, back in the 1960s, Howard Zimmerman's group was studying reactions of zinc enolates called a Reformatsky reaction. And Maggie Traxler and his group and Howard Zimmerman developed this model that explained everything that people didn't understand. And that is that you can get stereoselective aldol reactions. Because once you understand that lithium enolate formation prefers to put an R group down here, right? Remember that stereoselective lithium enolate formation, you'll end up with this methyl group anti to the oxygen. And so once you know that that alkyl group wants to be anti to the oxygen and the H wants to be closer to the oxygen, now you can predict, now that you know that aldol reactions proceed through this Zimmerman-Traxler transition state, which is a chair, you just have to say, well, I want to put big groups equatorial and I don't want to put big groups axial. So when you draw your aldehyde, you draw the H on the aldehyde with the H up here, and you draw the R group on the aldehyde down here in an equatorial position. And that is better than this. That's better than having the R group up here hitting and bouncing into anything that's coordinated to the lithium. Right? There will be other solvent molecules and other things coordinated to the lithium. That's not good. You want the R group on this, maybe I better make it R prime just to make it different, right? You want that aldehyde group not to be axial, you want it to be equatorial. So based on this Ireland transition state chair for telling us what enolate geometry we're going to make, when you combine that with the Zimmerman-Traxler transition state for lithium aldol reactions, boron aldol reactions, we have powerful tools to help us predict the stereochemical outcome of aldol reactions. So really powerful stuff, and this is kind of the mainstay for organic chemistry and CC bond formation. And just comes back to some of these same ideas we've been talking about. Negatively charged boron, negatively charged lithium, negatively charged silicon, donating into pi bonds. Now, what I haven't really talked about, and I don't know if this is totally obvious, is that an enolate has 2 reactive ends, right? If I draw an enolate like this one over here, there's the O minus of the enolate, and there's that carbon atom of the enolate. We would refer to this as an ambident or two-toothed nucleophile. It can react on either end, right? Why shouldn't something react with the O minus? Shouldn't the lone pairs just directly react? It feels to me like, haven't I been telling you, oh yeah, lone pairs? That's all the business right there, those lone pairs. So let's talk about when to expect that the oxygen of the enolate will attack and when to expect that the carbon atom of the enolate is going to attack. So here's a study somebody did just to assess what's the relative amounts that you get for the carbon atom of the enolate attacking in order to give you this CC bond versus how much of the oxygen atom is attacking in order to give you this CO bond. You'll sometimes see one or the other, but you have control over that. And the biggest thing that you can control in these cases is what is coordinated or not so much coordinated to the oxygen atom. What you can do is you can change the metal that's attached from there from lithium to sodium. So let me go ahead and draw out a series for you, and we'll see how that metal affects the relative ratios of C versus O alkylation. So I'm going to start off with the least electropositive metal. So what if it's a lithium oxygen bond on there? What if this atom over here, the M, is lithium, right? And if I march through the periodic table or down that row in the periodic table, and we'll be doing this a little bit in the next lecture too. If I go below there down to sodium, that's like right below lithium in the periodic table, and those alkali metals, right? Come back over here, and let's just march down this row to more and more electropositive atoms for those alkali metals. So I'll then go to sodium. What if I make a sodium enolate? What if I make a potassium enolate? Let me make that longer. I gotta satisfy myself here by making it look longer, weaker, less powerfully bonded. I mean, I'm not even sure we don't usually make rubidium anything. Maybe it's expensive. There's some reason why people don't use rubidium. Cesium, boy, there's not much of even a bond there. I'm not sure I'm even comfortable drawing. Let me not draw a full bond there. I'll try to draw it dashed or something. Sorry if you've already drawn that. I'll try to draw that dash because, there's just so far away, you don't get strong, powerful covalent bonds between cesium and oxygen. And if you wanted to have no bond whatsoever to that O minus, here's what you would do. You would use a tetraalkylammonium counterion. Tetrabutylammonium, right? That nitrogen cannot form a fifth bond, right? You put a tetraalkylammonium counterion on an enolate, and there's no bonding there. There's no interaction. That's a completely naked O minus. As you make that O minus more like, I'll just draw delta minus over here and delta plus. As you make it more like a naked enolate, you get more O alkylation. Right? As you walk through this series, you get more O alkylation, the more you put the negative charge on the oxygen. And if you have a lithium oxygen bond, a lithium enolate, those prefer C alkylation. That bond is pretty covalent, relatively covalent. More C alkylation. So we're pretty smart to use lithium enolates in organic chemistry and to avoid potassium enolates or cesium enolates. If you care about CC bond formation as much as I do, you're not going to be doing things with cesium enolates. You're going to be doing everything with lithium enolates if you want CC bonds. All right, let me try to summarize the selectivity, O versus C, for common electrophilic reagents that in organic chemistry. So if I take a typical lithium enolate and I add some alkylating agent like an alkyl iodide, you should expect that those are going to react faster. With a lithium enolate, they will react faster on the carbon atom of the enolate. It's this yellow atom that forms the bond the fastest, just like I showed you up above here. And so the eventual product after lithium exchange and all that other stuff would be a new CC bond. So when you make lithium enolates and you do SN2 reactions with those using typical alkyl halides, you don't have to worry about O alkylation. That's not a big issue. But what happens if we switch over to a carbonyl group like an aldehyde? Those lone pairs are pretty reactive. And the carbonyl carbon of the aldehyde is kind of like a carbon plus. There's like a fourth of a positive charge there. Now, if you were to see if the lone pairs on the oxygen were to attack some, you're never going to know that. That might be happening in solution, right? How would you know whether that's happening or not? Because if you did add on that oxygen atom of the enolate, you generate this kind of acetal type system, but that's not going to be stable. It's not like you're going to isolate that and work it up, because as soon as that oxygen of the enolate adds in, it's going to get pushed right back out, right, and regenerate the starting materials. So you're not going to be isolating any product if the O adds, so it's kind of irrelevant. We know what happens in these reactions that's irreversible. The irreversible thing that happens is that the lone pairs here on the carbonyl will add to there, and that starts that whole aldol process. Zimmermann-Traxler transition state. So when you take aldehydes and lithium enolates, the products of those reactions are going to be these the CC bond formation. You get bond formation there on the carbon. So we're not saying that the oxygen can't react with an aldehyde, but you'll never know. You're never going to know that. Now, what would happen if we took a more reactive carbonyl? Acyl chlorides are more reactive than aldehydes. They're more electrophilic. And now, if that oxygen of the enolate did react, now it's not going to go backwards, right? If we draw out the product for this process, we have this chloride leaving group here. Now when these lone pairs on the oxygen push downward, they're not going to push out the enolate, they're going to push out the chloride. And in fact, that's the product you get in this reaction. I wish I had drawn this in black, because everything else is in black. Just seems kind of weird to me that I drew that in red. But you get the idea. We're going to push out the chloride now. That's the better leaving group here. And this is in fact what you get. When you take acyl chlorides and enolates, you don't get C alkylation very much. We have to use special tricks to get C alkylation. The products that you get in these reactions are enol acetates. So I didn't mean to. This is the product you get. So if you wanted to make an oxygen-carbon bond, that's how you would do it with an enolate. You acylate it with an acyl chloride. Now the last species that I'll talk about is silicon. TMS chloride, TMS triflate, TMS whatever, with some good leaving group on there. Now we know silicon loves oxygen. I probably never said that in this class, but silicon loves oxygen. Anybody want to guess what's going to happen here? You know what's going to happen. It's the oxygen that's going to attack silicon. So you might get a little bit, and usually it's an annoyance of a few percent, but the main product in these reactions, I'm not going to draw the whole mechanism here. It goes through a siliconate. The product that you get is the silyl-enol ether. And those are synthetically useful. We use those in organic synthesis. Boy, silyl-enol ethers are useful because this carbon, whoops, I didn't mean to erase that, because that carbon at the end there is super nucleophilic. It's not just nucleophilic because of the oxygen lone pairs, but in other orientations, it's kind of like a allylsilane. So TMS silyl-enol ethers are useful. So when you silate lithium enolates or other types of enolates, you get oxygen-silicon bonds. So that should kind of be expected. All right, so depending on the reagent, you can react either at the carbon end of an enolate or the oxygen end of an enolate. Okay, let's shift gears. I don't know how much it's shifting gears. Maybe we're meshing a little bit. When I talk about this periodic table over here, and the lithium and the sodium and the potassium and the cesium, let's go into a little bit more detail. Carbon-carbon bonds are not nucleophilic. In general, you'd have to add an amazing electrophile in order to get any carbon-carbon bond to do anything. Maybe you'd have to have a carbenium ion right next door so you could get a migration. That's what it takes. But carbon-lithium bonds, wow, those are nucleophilic. Sigma bonds can be very, very nucleophilic. When you make bonds over here to this first column of the periodic table of alkali metals, those bonds are nucleophilic. So let's go ahead and walk through the periodic trends to understand what we should expect for the nucleophilicity of bonds to carbon. Right? We're interested in making bonds, doing reactions at carbon. And so let's just take a look at electronegativity. How does electronegativity and bond length affect the nucleophilicity of bonds to carbon? So if I want to pick the least nucleophilic bond to carbon that I can think of, it would be a carbon-fluorine bond. Boy, that is not a nucleophilic bond. Right, and I've sketched that down here in our MO diagram. right? Carbon-fluorine bonds, if you go from a carbon-carbon bond to a carbon-fluorine bond, right, those electrons are less reactive. They're in a lower energy orbital. Why? You would never want to take that carbon-fluorine bond and get it to attack anything. So this is the least reactive bond to carbon that we can think of, right? It's the least reactive. Fluorine, if you look at the electronegativities on this table, 4.0 electronegativity, it's the most electronegative atom, so that's going to be the least nucleophilic bond. If we went to a carbon-oxygen bond, it's still not reactive, but it would, if you had to make a choice, a carbon-oxygen bond would be more nucleophilic than a carbon-fluorine bond. We can just march across the periodic table. Unfortunately, my MO diagram goes vertically and not horizontally. But as we march across the periodic table, going to things that are less and less electronegative, more electropositive, what we do is we end up with sigma bonds to carbon that are more and more nucleophilic. And finally, when we get over here to lithium, I'm going to skip beryllium and boron, go right to lithium. Those bonds are high in energy. Those bonds are not as stable as carbon-fluorine or carbon-carbon. Those pairs of electrons are very reactive. So, so when we come over here and we draw a carbon-lithium bond, your expectation should be, wow, that's the most reactive of the bunch here. I'm going to write most reactive, but I'll put a question mark there because we've stayed in one row right now. What happens if we go to longer bonds? Notice what's happening to the electronegativity if I stay in that alkaline metal row. They all have electronegativities of about 1, right? They're not changing from 1 to 4. They're all pretty close to 1. The electronegativity is not really changing. It's the bond length that's changing. And we know what happens when we go to longer bonds. If I take a regular length bond like carbon-lithium, but then I switch to a longer bond, that bond is weaker. Those electrons are more nucleophilic. Go to carbon-potassium, that bond is even weaker, and so it's going to be more nucleophilic. Go all the way down to carbon-cesium, man, hard to imagine how reactive that would be. I've never seen anybody make an alkyl cesium compound, never heard of it. It would deprotonate your solvent or do other weird things that you couldn't. It's just so reactive it's not useful. It's not, we don't discuss those types of things. Or even alkyl, we'll talk about this, alkyl sodium. Like you don't make butyl sodium as a reagent, it would just be crazy reactive. So we usually stop here when we make reagents. And we also, as you know, we make organomagnesium reagents, Grignard reagents, that's pretty common as well. Okay, so really the most reactive bond, too reactive actually, I'll just say too reactive, most and too reactive would go together, would be a carbon-cesium bond. Let me just draw this really freakishly long. Someday you're going to come back to me and you're going to say, Van Vranken, you told us these bonds are super long and super, and you'll find that they're not that different in length, but they're different enough. I usually use bond length as a way to describe orbital sizes. Yeah. Say that again? I think we'll talk about this shortly. Dative is used for, the question is this carbon-cesium bond more like a dative bond? No, as long as I draw it with the correct charges, it's not a dative bond. The dative is a rep, we'll get to this in a second, talking about the Sure, yeah. So the question is, can you make a carbon-calcium reagent, like dimethyl calcium? Again, that would be a super reactive reagent, and it would offer no benefit. And we'll talk about the cost-benefit ratio as you make bonds from lithium, which is really the one you want, to bonds that are in lower rows of the periodic table. Yeah.
How would they transition metals in terms of like in terms of like the reactivity?
You'd end up with longer bonds that are weaker, but they're not very polar. So you wouldn't get the advantage of, right? You wouldn't get the advantage of going over to this side of the periodic table. You know, there's an advantage to going to a very electropositive things. It really soups up the reactivity. So most carbon metal bonds, carbon iron, carbon manganese, carbon cobalt, are not very nucleophilic. You could add aldehydes, and they don't do Grignard type reactions with typical carbonyl compounds. All right, so let's just talk about this, like ideas. We'll get to dative stuff in a second, but when I draw a carbon-lithium bond, when we teach out of typical introductory organic chemistry textbooks, There's two representations that are common. One common representation for a carbon-magnesium or a carbon-lithium bond is just to draw a line there. And that's a great Lewis representation for a carbon-lithium bond. There's another representation that is used, and that is to take the electrons over here that's in the bond and give them to the more electronegative atom. Now, how would you know which atom is more electronegative? Well, you've got to know the periodic table. There's no short, either you memorize all the numbers or you kind of get to know where things are in the periodic table. If you want to draw a good resonance structure, give the electrons to the more electronegative atom, and you have to know relative electronegativities to make that decision. So going back to that table I showed you before, you need to know, that the electronegative atoms are over here and the upper right-hand corner of the periodic table. Okay, so Linus Pauling, so there's a problem with drawing things in this ionic form. Not just that it adds extra work to you. And that is, this is only a resonance structure. Notice how I'm drawing a resonance interconversion arrow here. This is only a resonance structure if I put the lithium and the carbon exactly the same distance as they were when there was a bond. If I move it even slightly, it's not a resonance structure anymore. It's only a resonance structure if the atoms stay exactly the same distance. And so when somebody draws this, that's not usually what they mean. Usually what they mean is, oh yeah, the lithium has popped off and is like moving all over the solution, and they're floating around and they're not near each other. That's completely ridiculous. Methyllithium doesn't do that. It does not. The lithium and the carbon atom are bonded. We'll get to that shortly. So this idea of things ionizing and having no bond is kind of crazy. And you can kind of trace back the origin. Why did people talk about this even? What is it? Why would anybody write a textbook where they do things like that? Well, Pauling, long ago, Pauling, Nobel Prize winner, 2 Nobel Prizes, really thought a lot, wrote a book on the nature of the chemical bond. And he pointed out, he's the one who developed this electronegativity scale, the most common version of the electronegativity scale that we use. He made the statement in that book where he says that you can consider a bond to be 50% ionic. A bond is 50% ionic if the difference in electronegativity is 1.7. If the difference is 0, carbon-carbon, well, it's solid covalent. But if you have carbon to lithium, now there's a difference in electronegativity. And Pauling said you can just subtract the 2 electronegativity numbers. Carbon is 2.5, lithium's about 1, it's about 1.5. He said a bond is 50% ionic if the difference in electronegativity is 1.7. All of these are about 1.7. All of these bonds are about 50% ionic bond and 50% covalent bond, according to Pauling's. Now, when you come over to an electronegative atom like oxygen over here, oxygen, that's 3.5 electronegativity. That's much more electronegative now. And lithium is still electropositive. The difference there is substantial. These bonds are mostly ionic, according to Pauling. These are greater than 50% ionic. I don't know if you can actually calculate the exact percent, but they're more than half ionic. But you know what? Linus Pauling didn't say there was no bond. He said there is a bond there, and the bond is 50% ionic. So Linus Pauling never said that they ionize. He never said this. He said there's a bond there. So if you want to choose a representation, this is the representation that you should choose. There's a bond, and the bond is 50% ionic. So here's one of the reasons why people like to give the electrons to the more electronegative atom. Because if you see a representation like this and you start arrow pushing, everybody knows where to start the arrow. You start from the thing that is the lone pair. So that helps people who are just struggling to remember electronegativity. And maybe in some case you may end up in a situation where you're looking at something like this and you just don't know the electronegativity. It's like, what? I frequently see people push arrows and they form the bond to the wrong atom. When I start my arrow like this, you can't actually tell, am I going to form a bond to the K or the germanium? Potassium or germanium? You don't know yet. It's not until I draw the products. How would you know? Well, the way you know is you want to take the electrons away from the electropositive atom. You want to keep the electrons on the electronegative atom. So in this case, germanium is more electronegative. Whoops, more electronegative. I want to make sure that that germanium keeps the electron. So when I draw the new bond, that new bond better be still attached to the more electronegative atom. That's germanium. There's the new bond. And I want to take the electrons away from the more electropositive atom. It's happy being positive. So you need to know your way around a periodic table and know those electronegativity trends in order to make decisions. At some point, you'll be like me. It's like, geez, I've just seen bonding. The bond is always to the carbon and not to the lithium. You forget that the periodic table predicts this kind of stuff. But you want to make the bond. You want to make the bond to the more electronegative atom and take the electrons away from the more electropositive atom. So that's a dead solid rule. All right. What does methyl lithium really look like? I told you don't draw methyl minus and lithium plus. That's ridiculous. It doesn't do that. Here's what methyl lithium looks like in solution. It looks like this. That's what methyl lithium looks like. We know from crystal structures. We know from ab initio calculations. How many bonds are there to that carbon atom? There's 6. That's what methyl lithium looks like when you put methyl lithium in solution. I hear people talk about, Texas carbon, you can't have 5 bonds to carbon, or what. Hey, I'm from Texas. In Texas, we know that what really drives organic chemistry is the octet rule, not some kind of, sophomoric rule about the number of bonds here. As long as the carbon doesn't violate the octet rule, we're good here. We're good. So let's try to make sense of what we're looking at in this structure. All this weird-looking structure here is driven by the fact that lithium wants 8 electrons. Lithium is insanely desirous of having 8 electrons. It doesn't want 2 electrons, right? This is 2 electrons in lithium. That's no good. And still in this structure, the lithium only has 6, but you're getting close. So if you walk through all the charges and draw a Lewis structure takes charges into account. You assign correct formal charges. If you don't assign correct formal charges, it is not a Lewis structure. And the advantage of a Lewis structure is you can do arrow pushing and all your charges will work out. So Lewis structures are good for arrow pushing. There's another way to represent these. Sometimes people get frustrated drawing all the minus charges and the plus charges. It gets crazy. It's like, gosh, I can't handle all those minuses and pluses, and I totally agree with you. So oftentimes in organometallic chemistry, people don't want to draw rhenium minus 7, so they draw dative bonds. They don't take into account, typically in organometallic chemistry, people don't take into account the formal charges on their structures, and that means you cannot use these bonds. These are called dative bonds. It's called a dative representation. When you don't keep track of charges, don't use those for arrow pushing. In dative structures, if you try to push arrows with those, you'll get the wrong resulting charges on your product. So not for arrow pushing. But it sure does look simpler without all those minuses, -2, +2, all those charges. Now, how do you make sense of a structure like this? It's like it just looks so strange and different from anything we've ever seen before. If you wanted, you could get to these kinds of structures. You just have to be. So how do you think about why lithium forms a tetramer? Well, I told you already that lithium wants 8 electrons. So if you have a lithium atom with only 2, it starts to become reasonable that maybe one of these H bonds, the CH bonds, can donate electrons into the lithium. Now, I can't take the electrons away from the C, and I can't take the electrons away from the H. But when I get to this next structure, right, I'll end up with a bond to lithium, and I have to keep track of charges. It will be lithium minus and carbon plus. And this other carbon atom that's nearby, right, also has H bonds on there. And those CH bonds can donate into the neighboring lithium, just like this. Right? You start to get square-shaped dimers. And then there's still more methyl lithium, and that's the only thing that's in solution is methyl lithium. And so then you'll start to see more bonds forming. And eventually you're going to get to these cube-like structures. The alkyl lithiums form cube-like tetramers, they form hexamers, just desperately trying to give lithium 8 electrons. They form these aggregates in solution. So it's frustrating. I'll simplify our situation shortly. It's kind of depressing to think about this. What are we going to do in our class? How are we going to handle the fact that organolithium compounds, organomagnesium compounds want to form these kinds of aggregates? Well, we're just going to kind of ignore that, really, is the reality. So here's how I want you to push arrows. I don't want you to draw out the aggregation, so if you have a Grignard reaction, just do it like this. Isn't that what we've been doing? That's pretty simple. Use the bond to make bonds to R. If it's an ethyl group, the carbon is more electronegative than magnesium, so you're going to make a bond to the R group. If it's a phenyl group, the phenyl carbon is more electronegative than magnesium. So I expect you to keep doing exactly what you've been doing when we make bonds. So in this case, our next structure would, right, this is the way we should continue to push arrows in this class, I hope. We'll have this bromomagnesium cation floating around. So you get the idea. So this is the way I want you to push arrows in this class, is keep pushing them, hopefully the way you've been pushing them in this class. That's the way we've been representing reactions of Grignard reagents and organolithium reagents with carbonyl compounds. Now, what I don't want you to do in this class is draw the resonance structure. I don't want you to do this. Right? As long as I keep those same distance, magnesium versus carbon, yeah, in theory that's a resonance structure, and in theory you could add that to the carbonyl, but how does that save you any time? How is it easier for you to draw two dots and a minus and a plus than to just use the bond that was there? That is not simpler. It's easier and faster just to draw an arrow with the bond. Instead of first drawing some sort of a resonance structure and then promising me that, yeah, that you did keep them the same distance apart. You didn't actually float the magnesium away. So this is, don't do this. I'll just write no. Don't do that. It's not realistic. Okay, but let's be honest about what's realistic and what's not realistic. Let's talk about the actual mechanism for addition of methylithium to a ketone, like acetone. Turns out that the actual mechanism involves the dimer. Yeah, there's tetramer in there, but some of it exists as the dimer. And lithium wants 8 electrons, so sometimes that tetramer cube thing dissociates. And whenever the carbonyl of a carbonyl compound coordinates, you end up eventually forming another bond to lithium and then breaking one of these carbon-lithium bonds, like this one right here. And that positions this carbon-lithium bond 6 atoms, this R lithium bond, 6 atoms away from the carbonyl. That's the correct mechanism. We're not going to draw that in this class. Do not draw that in this class, but don't forget it. Don't forget that alkylithiums form aggregates. They form tetramers, they form dimers, and it's so satisfying to see that because it looks kind of like that Zimmermann-Traxler transition state. So what I'm telling you is in this course, I want you to remember that that aggregation is occurring, but we're going to continue in my class, if you want to get the points, to draw organolithium additions like this. Use the bond, don't draw it C minus lithium plus, and then attack. Right? That's how we're going to continue to push arrows in this class. Don't forget that alkylithiums aggregate, but we're going to draw it as the monomer because it's just drawing all those formal charges just becomes too complex. So, so hopefully this is what you've been doing, right? This is hopefully the same thing you've been doing with Grignard reagents and alkylithiums and other reagents. Is just use the bond and attack the carbonyl. We don't need to draw those aggregates. You might think that that aggregates are somehow special for the alkylithium, but it's not different for potassium. We've probably drawn out in our arrow pushing mechanisms, maybe because I thought it would freak you out, stuff like this. That's not what potassium T-butoxide looks like. We know the structure for potassium T-butoxide. We have solution structures, crystal structures. Is it a surprise to you that potassium T-butoxide exists as tetramers and hexamers? Things where the potassium atoms have more than just one bond. Because potassium wants to have more than 2 electrons. It wants, it's trying to push for some valence of 8 electrons. So this is the crystal structure of potassium T-butoxide. When you put it into solution, you find that potassium T-butoxide aggregates. And what you find is that in solution, it never looks like this. It doesn't look like potassium minus K+. That's not what potassium T-butoxide looks like. So when you push arrows with potassium T-butoxide, we'll get to this shortly, you don't draw it as TBuO minus. You don't need to do that. It's not going to save you any time, I don't think. And we'll see the same thing with lithium oxygen, lithium alkoxides, or lithium enolates. When you draw a lithium enolate, let me urge you, do not draw lithium enolates like this, where the lithium is plus and the O is minus, right? After all this stuff we said about the Ireland transition state, where you want this bond here to explain what's going on when you deprotonate. When you deprotonate to make lithium enolate, you need that lithium oxygen bond in there. If you talk about stereoselective aldol reactions through the Zimmermann-Traxler transition state, you need this lithium oxygen bond there. So, if you draw an enolate out, you might as well just draw, right? Go ahead and draw that lithium oxygen bond. Right, that's the way to do it. Not like the charge separated thing. And once people understood that, there's a covalent bond there, it's just everything falls into place in the field of organic chemistry. It does make it more complex to draw things out. And again, over here is the structure for a lithium enolate in solution. It exists as this mixture of hexamers, dimers, even monomers in small amounts in solution. Okay, so when we push arrows with potassium T-butoxide or sodium ethoxide, here's how I want you to do the arrow pushing in this class. Now that we've had our discussion about this, go ahead and draw the bond, but then when you do the arrow pushing, use the lone pairs. Right? Carbon alkylithiums didn't have a lone pair on carbon, but oxygen has a lone pair, so use it. Use the lone pairs. That's what we've been doing. And so that'll allow you to make a proton. And then in a second step, we can ionize this to release a potassium ion. I'm not taking a bond and separating to give minus and plus. There was a plus on the starting material here. See, there's a plus on the starting material, and there's a plus in the products. I'm not creating any charge separation there there was already a plus in the starting material. So in the second step, you can release a K plus if you want, because it's not going from a neutral bond between neutral atoms. So here's, again, what I don't want you to do is take a bond between two neutral atoms and do this. Don't do this thing over here, right? That's not really realistic. Don't take that bond between two neutral atoms and separate the charges. That costs energy. Coulomb's law would tell you how much energy it takes to separate those charges. So that doesn't really help you to get anywhere. If we're trying to deprotonate on next to a carbonyl group or something like this, don't do it like this. This is not the way. This is not the way to use it's not a realistic representation of what's going on with alkoxides. Also, you might say, oh, well, he doesn't want us to separate the charges. Maybe I'll just use the bond directly without separating the charges, like this, down below here. Like maybe I'll just start with, well, no, just use the lone pairs. There was lone pairs on there. It's the lone pairs that are the reactive part of that species. Use the lone pairs, so don't do that. Use the lone pairs. That's what we want to do, yes. That's just like up above. Don't use the bond, use the lone pairs. Now, in reality, the potassium doesn't just fall off because potassium wants 8 electrons. I've shown down below here a more realistic representation. You shouldn't do this in this class because our mechanisms will take way too long for us to draw out. But in reality, the potassium doesn't just fall out. Some other species, THF or your enolate or something, will come over and help that to leave by doing an associative mechanism. This would be the realistic representation for how you get that potassium off of there. But that's just too much work. In this class, I will allow you to take a positively charged species with potassium on there, like this, and simply dissociate the potassium. That'll make our mechanisms much simpler. If you want to do this, you are free to do that, but your 10-step mechanism will turn into a 20-step mechanism really quickly. And that is not worth our time in this class. Okay, so what are some other species that are bonded to sodium, potassium, those alkali metals? Well, metal hydride reagents, sodium hydride and potassium hydride in particular, are common reagents that we use in organic synthesis. And what do they look like? Well, they don't look like hexamers and tetramers and things like that. If you've ever used these reagents in the lab, you know they're just gray insoluble powders, and they do not dissolve in anything. They don't dissolve in anything. These things are these cubic lattices, And there is no such thing as a sodium hydride molecule floating around on its own that is not attached to 10 million other sodium hydrides in one of these crystal structures, in one of these cubic structures. But for arrow pushing in my class, we're just simply going to pretend that they are monomers, because we cannot draw all these dative bonds and charges and other stuff. We're just going to pretend it's a monomer, and you're never going to forget that it's actually a solid and everything's occurring on the surface. So when you draw acid-base reactions using sodium hydride, potassium hydride, metal hydrides in our class and use them as bases, just draw it as a monomer. That's the way we're going to do it. And someday when your reactions aren't working, you're going to remember, it's like, oh yeah, they're not soluble, so the concentrations are low, and that's why my reaction's not working. Okay, now when you see these bonds, sodium hydride, potassium hydride, wow, there's such powerful reagents, because when you deprotonate things like alcohols, you end up generating hydrogen gas, and that floats away. These are irreversible, because the hydrogen gas floats away. It's not going to come back and regenerate the sodium hydride bond. So you'd think with a powerful reagent like that, it ought to be a powerful nucleophile. Well, no, it's not a powerful nucleophile. These are powerful bases. They're good at deprotonating, but not ever. Not ever in this class, not ever that you will see, not ever do they act as nucleophiles to attack carbon. They're just used for deprotonation to generate hydrogen gas. That's what they're used for. Now, all metal hydrogen bonds are not created equal. So if I come over here and I compare, I wish I had drawn this a little bit differently. If I compare lithium hydride, can't remember I've ever seen anybody use that, sodium hydride and potassium hydride, guess what happens to the reactivity as we go to longer and longer bonds? Take a guess what's going to happen. You know it's going to be more reactive when we have weaker bonds, longer, weaker bonds. So I'll give you some relative numbers here for these metal hydrides. I'm going to assign a relative basicity. So if you look at the relative rates at which these things deprotonate, we don't use them as nucleophiles. So you'll never see this. You'll never see, right, that's crazy. Sodium hydride would never do that. That's not what those things do. What they do is they deprotonate next door. That's what they do. They deprotonate. I'm not saying I would ever do it for deprotonation next to a carbonyl either, but if you, okay, so sodium hydride, lithium hydride, potassium hydride can deprotonate, and they're not all equally reactive. Lithium hydride is the least reactive of these. I'm going to assign those a relative rate of 1, and sodium hydride with that longer bond is 1,000 times more reactive, right? Would you rather spend an hour in the lab or 1,000 hours in the lab? You'd rather spend an hour in the lab. You'd use sodium hydride. I've never seen anybody use lithium hydride. I don't even know, do they sell that? Who would buy that? That'd be kind of dumb. But you know, if you really want to get out of the lab quickly and you really want your reactions to work, I mean, the problem with sodium hydride is it's an insoluble powder that's sitting on the bottom of your flask. Very little of that is exposed to your reactants. So if you really want fast rates, since it's almost all insoluble, you should switch to potassium hydride. That's the stuff. Potassium hydride. Problem with it, yeah. The question is, do they sell tert, butyl, ammonium? Oh, tetraalkyl ammonium. So the question is, do they sell like a tetraalkyl ammonium hydride with no bond? It would be too reactive. The problem with, so the question is, could you have something like some tetraalkyl ammonium that can't form any bond at all? There's a couple of problems here, and one problem is that these protons right here, bases can pull those off to make an ammonium ylide where you have plus and minus next to each other. The other problem is that there's also beta protons. You'll get beta elimination, and so just even if you have tetraalkyl ammonium hydroxide, you see these side reactions occurring. Okay, if you're ever in the lab and you want to do a deprotonation, every time I've used potassium hydride, I've had a fire, because when you quench it, the hydrogen gas from the water ignites and causes a, but I've never been sad that I used potassium hydride. Yeah?
What about cesium hydride?
Never heard of it. That would be too crazy. Okay, we have reached the end of our time here. I've gone over time. Potassium hydride, man, that's the stuff.